Okay, let's wrap up our series on weather theory. In this short video, we're going to cover weather considerations that we haven't looked at yet, including things such as turbulence, icing, wind shear, fog. It's important to note that all these considerations, again, are just the byproduct of the air mass you're flying through and its weather characteristics, its atmospheric stability or instability, and moisture content. Everything we've covered thus far still impacts the type of weather and will determine what type of weather you're flying through. So it's important to understand the fundamentals first. Will greatly enhance your ability to plan for weather events and things of that nature. So let's dive right in. Every day, as weather events occur, you hear things on the news. I particularly like that top right pic. I don't think that plane's going flying anytime soon. But yeah, you're always hearing about how specifically, the airlines are dealing with different weather events because more or less the aircraft that they fly in the airlines are designed to handle many different types of weather events that some of the light planes that we fly are not. But still, they run into some situations that I'd say they can't potentially handle as well. So we're going to look at a few different considerations, icing, low visibility, things of that nature, and we'll touch on how each one of them can affect your flying. Let's look at turbulence first. Now, throughout our flight training, we rarely ever find ourselves in a situation where we are flying in the conditions that you might be introduced to major turbulence events, but nonetheless, you have to be prepared for them, and it's good to talk about them. As you might imagine, and I hope I'm not beating a dead horse here, but turbulence is caused by atmospheric instability. You will not, I shouldn't say never, but you most likely will never run into turbulence in a stable atmosphere that's characterized by things such as low moisture content, dry, cool air, and stratiform clouds. So think of warm air mass, warm front, where you have the sufficient atmospheric stability that you don't have a lot of vertical development. That is an air mass where you'll have very, very little turbulence. We've already covered in the last lessons that you can expect cumuliform clouds, large temperature difference with altitude, or large lapse rate. You can expect these things in an unstable atmosphere. And so when you have large temperature lapse rates, for example, let's just kind of talk through this from a physics perspective. If you're flying in the atmosphere and at your altitude, it's 50 degrees. Now let's say 1,000 feet above you, it's 45 degrees, which would be a 5-degree temperature lapse rate. That is significantly convective. That's a very, very large temperature lapse rate. Air is going to be rushing. Warm air, the 50-degree air, is going to be rushing towards the 45-degree air. It's going to be rushing up. You'll have extremely extensive vertical movement of air. That is what you're feeling. You're going to feel that in the airplane. That'll be your turbulence. As that air goes from warm air to cool and starts to vertically develop, you're going to feel that in the airplane. That's going to negatively affect the air patterns around your wings. It's going to cause turbulence. As you're flying through pockets of atmospheric instability, you're going to be dealing with what we call clear air turbulence. That's flying through areas of the atmosphere where the wind patterns and the air patterns are wreaking havoc on your airframe. What are you going to do? You really need to think twice about flying through, obviously, areas that could be significant vertical development. So we've talked about hot Texas day, white puffy cumuliform, cumulus clouds, potentially the beginning ingredients of a cumulonimbus thunderstorm cloud. you want to really avoid flying your airplane through those clouds. That, you know, you're going to find extensive vertical development, vertical movement of air, and your airplane's going to feel that. So first and foremost, avoid cumuliform clouds if you can fly around them. Operate your aircraft in the green range on your airspeed indicator. That's the normal airspeed range. And if your aircraft has a published maneuvering speed, operate your aircraft below the maneuvering speed. That will help you that'll help your airframe withstand the stress of the potential, turbulent movements of the air. Check in with your passengers. Once you have your private pilot certificate, one of your responsibilities is ensuring that you're, able to safely operate the aircraft with non-certificated people on board. So anytime you're in turbulence, unless you're flying with a pilot or someone who loves to fly in turbulence, you might want to check in and make sure your passengers are doing okay. And, finally, maintain a level flight attitude. You want to fly straight and level. You want to turn off the autopilot. You want to hand fly the airplane. I have a note on here about banking the airplane. We've talked about in aerodynamics, when you bank the airplane, you're increasing the load on the aircraft's wings, on the airframe. Well, if you have an increased load on the aircraft by banking it, and then you get hit with a gust, a turbulent gust, well, that further increases the stress on the airframe. They're further potentially increasing that load factor. And of course, your airplane's only designed with so much load factor. So if you're in that cumulus cloud, if you happen to find yourself, in range of a thunderstorm and have turbulent air, you want to maintain straight and level attitude. Check on your passengers and make sure your airspeed is in the green range, preferably below your maneuvering speed. Talked a little bit about wind shear earlier when we were discussing thunderstorms. Wind shear, which can be identified as turbulence. Wind shear is a sudden change in wind direction and speed, or speed. And it really is, it's just the sudden shifting of the Earth's air currents, the air currents of the atmosphere you're flying in as you fly, from point A to point B. So you could be flying along at 6,000 feet, cruising with a headwind of, 15 knots, and then you fly through an air pocket that has a different, maybe different wind direction and speed, and maybe your headwind will shear to a tailwind. Now you've got a tailwind to deal with, or maybe the opposite. Maybe you're flying with a tailwind, and then all of a sudden you encounter a headwind because you've got a shear of wind that you're flying through. It can really, really happen at any phase of flight: takeoff, cruise, landing. We want to be extremely careful of wind shear situations when we are low and slow, so approach to landing, things of that nature. And so I've got a couple graphics on this slide that we can walk through from an example standpoint, and you can see this is an example of an airplane that's coming in for landing. And so right here in this first example, I've got a aircraft coming into land and encountering a headwind shear. So, maybe they were coming into land with like a 5-knot headwind, and a gust of wind, a wind shear hits them like a 20 to 30 knot headwind. And so what we have to do is just think about this from the aircraft standpoint. What the airfoil, what the wings are going to see from a relative wind perspective. You're going to basically be going from a pretty calm headwind situation to a pretty aggressive 20 to 30 knot headwind situation. So immediately the airplane is going to see an increase in velocity of air moving across the airfoils. We know that velocity, part of our lift equation, as velocity goes up, lift goes up. So the airplane's going to feel a momentary increase in lift. It's going to potentially pitch up and try to fly in a more of a nose up, high angle of attack type lift attitude. And so as a pilot, you have to be ready for that. you're going to obviously see a potential increase in indicated airspeed, which would be that shear hitting the pitot tube. And you can expect really an increase in lift performance. You know, if you're if you're flying on a glide slope, if you're trying to maintain a approach glide slope, normal descent rate, that's going to be difficult to do, right? Your airplane's going to climb above the glide slope. I've got a couple notations here, you know, true airspeed, you know, the speed at which you're traveling through the specific air mass is going to, you know, momentarily increase and then kind of stabilize out as your airplane stabilizes with that new wind value. But as you might imagine, with that increased shear, your ground speed is going to dramatically decrease. And so as you're flying towards the runway, it's going to look like your airplane's having some trouble getting to the runway. So, so that's one scenario. And then another scenario, and potentially, I would say, the more dangerous scenario. I mean, wind shear of all types is dangerous close to the ground regardless. But, you know, this one may be more dangerous than the first scenario, is when you're flying low and slow, approach to landing, you're coming into land, and you have a constant headwind, and you encounter a tailwind wind shear, where now the airplane no longer has that headwind. Instead, you've got a constant tailwind to deal with. Again, let's think about let's think about this from the standpoint of the airframe itself. You know, the airspeed of the wind, relative wind going over the airfoils was one value, and now the relative wind speed going over the airfoils is going to be much less because the shear factor, right? Originally, your true airspeed might have been, you know, 110 knots. And now your true airspeed through that specific volume of air might go down 10, 20 knots. And what that looks like to the airframe is a loss of lift performance. Again, velocity of the air going over the airfoils is part of your lift equation, and as that velocity goes down, your lift goes down. So what does that mean for the airplane? If it's no longer producing as much lift as it once was, it's going to descend. Just as if you slowed the airplane down in normal cruise flight, the airplane's gonna want to descend. So in this scenario, with a loss of lift, the airplane's going to fall below the glide slope. It's going to have less lift performance. You as the pilot might be inclined to pull back to save your glide slope or save your altitude, which could further aggravate the airflow over aggravate the situation as it regards to air velocity over the wings. And you may, you may encounter or approach stall speed. So that's why I say this one is a little bit more of a dangerous situation. Now, your ground speed will increase, so you'll approach the runway at a faster speed, but that really is not as important as staying on glide slope, having a safe protection from obstacles close to the runway, etc. Something to keep in mind. Really the best way to visualize and interpret the wind shear scenarios on landing is just think of it from your aircraft's wings and airfoil standpoint. What is the wing scene? What are the physics associated with the airflow over the wing? And then you can kind of determine what the airplane is going to do from there. As far as flying in an area of potential wind shear, let's say there's a frontal boundary moving through the area, or you have a change in wind direction due to different weather patterns moving around, or hey, maybe a thunderstorm is local but not local enough to impact your approach to landing. Well, you want to come into your approach to landing with more power, more airspeed. You want to be ready for a go-around, potentially if the shear is bad enough. But if you're flying a light single-engine aircraft approach to landing, you want to maybe have a higher approach, depending on the runway length that you're dealing with. Higher approach, higher landing speed. You want to be able to compensate for any sort of potential wind shear event that your aircraft's wing airfoils are going to have to deal with. A couple other notes on wind shear. Just when you're in cruise flight, obviously, you're going to be looking for different types of wind shears around frontal zones, different air masses, cold air masses, warm air masses. We talked about thunderstorms. There's jet stream turbulence, which is more for the guys flying up in the flight levels. Here, you want to definitely think about some of these bullet points, when you're considering approach to landing, which is, approach to landing, takeoff, just very important when you're low and slow to the ground. We talked about staying away from thunderstorms 20 nautical miles away. We talked about higher air speeds. When we get into some more ground school on weather reports and the tools that you can use to determine where bad weather might be along your route of flight, there's actually some tools available to help us determine where wind shear might exist close to your destination airport. So more on that later. Let's talk a little bit about another type of phenomenon out there, and that's icing. And similar to the ingredients of a thunderstorm, it's important to note that there is specific ingredients for icing as well. You have to have visible moisture, so you're not going to encounter any icing if you're flying on a clear blue day and you have no moisture outside the airplane. And the second ingredient, obviously, is the temperature of the aircraft surface will need to be below zero. So what we're looking for essentially is an outside air temperature near or below zero, and we're looking for visible moisture as the necessary ingredients for icing. And really, what does this mean for the private pilot? Obviously, you need to be considerate when you're flying through clouds. Say you're instrument rated and you're on instrument flight plan, and your route of flight is going to take you through clouds, which by definition fits into number one, areas of visible moisture. You need to know what type of clouds you're going to be flying through, what type of temperatures you'll be flying through, and understand various weather patterns along your route of flight. So let's maybe talk about an example. Let's say I'm flying from Fort Worth to Houston this weekend, and I'm taking my Cessna 172, which does not have any sort of de-icing or anti-icing equipment on it. And the weather on Saturday is supposed to be pretty bad. It's going to be, warm front type precipitation. It's going to be gray and rainy. I'm expecting stratiform clouds. And so we talked earlier, stratiform clouds are generally high moisture content, okay? So by definition, we are now looking at number two there on the screen. Number one. So I'm going to be flying through some clouds with some sufficient moisture. So it's going to be prudent for me during my flight planning to take a look at the temperature profile of my flight and where, what altitude I'm going to be flying at, etc. So I'm going to be very keen on understanding where the freezing level is for my route of flight. Now, I've kind of already looked ahead, and even though I'm going to have to probably look this, the morning of my flight as well, but I've looked ahead to the forecast for tomorrow and found out that the freezing level for my flight is actually going to be at 12,000 feet. Well, I wasn't planning on flying that high. I have my cruising altitude planned out at 6,000 feet instead. So what do I know now? Well, I know that I'm going to be flying through areas of visible moisture potentially. because it's going to be a gray, rainy, stratiform type cloud that I'm going to be flying through. But I'm going to successfully avoid number 2 there. I'm not going to be flying in an area of freezing temperatures. So what this tells me is I probably pretty low risk for icing along my route of flight. Now, if this was up north in the wintertime, like maybe I'm flying from Chicago to Indianapolis in February, and let's say same scenario. Let's say I'm flying through a area of stratiform clouds, which high moisture content, and let's say I'm flying through maybe a frontal boundary. So I'm going from maybe a warmer air mass, to a cooler air mass, and let's say that frontal boundary has some more weather characteristics along it, like freezing rain or snow, or some precipitation events. I would be very keen, especially in the wintertime, to check out where that freezing level is, because to be honest with you, in February in Chicago, there's a very good chance that freezing level is at the ground, and it could be below freezing at the ground. So just some things to keep in mind as we consider icing. But the two big things to really pay attention to: visible moisture and freezing levels, outside air temperatures. And you want to really have a keen sense of those specific items along your entire route of flight. If you do encounter icing, you want to be very cognizant of how that affects the aircraft. Just because we do a very good job of planning our flight out from a weather perspective doesn't mean things, surprises don't happen. And so, ice on the airframe is going to do a couple things, and none of it's real scientific. Because you just never know what's going to happen. But in general, it's going to add some weight to the aircraft, to the airframe, weight that, you didn't plan for, weight that wasn't there before. And your airplane's going to be, extremely less aerodynamic. I mean, the airfoils are designed to produce lift based on the shape that they're formed into, right? And ice on the front leading edge, over the top of the wing, just really messes up the boundary layer physics for the wing. It creates eddy currents and different types of aerodynamic phenomenon that the airplane just doesn't want to deal with to produce lift. And so really that's the primary concern when you're accumulating ice, is the lift devices on the aircraft become less and less aerodynamic. They don't produce as much lift as they can. And so, what do you need to do? You need to be very cognizant of your airspeed, because as your wings produce less and less lift, by definition, your stall speed is going to go up, and the airplane is going to stall at a higher airspeed. So you need to be very, very cognizant of the configuration your airplane's in, where the nose is. You want to maintain altitude, maintain straight level flight, and increase your airspeed if you can. You want to get as much airspeed over those wings as you can. And so obviously declare an emergency if you have to, find a place to land, find a place of warmer temperatures if you can, climb out of the visible moisture, descend out of the visible moisture if you can, looking for ways to eliminate numbers 1 and 2 there on the screen. So hopefully no one has to find themselves in that situation. Finally, we'll touch on one of our last weather characteristics we'll talk about is fog. And again, fog, it really just, it's not a shiny new object. It simply is just regurgitation of some of the fundamentals we've talked about relative to clouds, really. What do you need for fog to form? Well, you need moisture, because in order to have visible moisture in the air, or in order to have a cloud, you need visible moisture. The moisture has to reach the dew point. Specifically for fog, we're talking about an air mass where the dew point and the moisture sufficiently reaches the dew point close to the surface. And so it's simply just clouds forming at the surface. And the FAA is going to want you to kind of understand different types of fog definitions, how they form, how you can potentially forecast the existence of fog. Now, I'll tell you, when it comes to weather forecasting, Fog happens to be one of those phenomenons that is somewhat difficult to forecast when it comes to specific locations. You know, the weatherman will be able to tell you that there will be potential for fog, and you'll be able to see on your weather forecasting tools where fog might exist. But it is not one of those phenomenons that is extremely pinpoint accurate. You know, fog is going to generate right here over this airport, or it's generally still one of those things where they have a more of a area forecast or broad locations where they say, hey, there might be some fog tomorrow morning, or you know, the conditions will be right for fog. But let's walk through each one of these one by one. First, we have radiation fog, and as we go through these, I'll kind of talk through some of the, you know, the weather physics, what's going on. Radiation fog is really simply when the ground, you know, the ground itself, the Earth, cools faster than the air does, and so the air surrounding the ground cools down to the dew point. Okay, once it hits the dew point, it will condense. The moisture in the air will condense and form that fog. It's key to know that the radiation fog typically will not form if there's a lot of wind, or if there's any wind at all. So what we're looking for here is not a lot of wind and a high moisture content in an area where the ground will cool very, very fast. So think about ground cooling on this one. Radiation fog, ground cooling. Steam fog. Steam fog forms over water, and so you'll notice this if you're driving down the road in the early morning hours as the sun comes up, and you'll look towards bodies of water and you'll see fog forming over bodies of water. Well, that's steam fog, and that forms as cold air passes from land over water, and that cold air that doesn't have a high moisture content comes over the water and becomes moist. Essentially, the water evaporates into that air, and by doing so, the air is already at the dew point, and it condenses immediately, and so that's how that fog forms. Advection fog. And the popular, I'd say the most popular example of this is on the West Coast, the fog that forms in and around the coastal areas of San Francisco and Los Angeles, sometimes called the June gloom. Advection fog is formed when warm and moist air from the water meets the land. And in this case, advection fog, you do have to have some air currents. You have to have some sort of a sea breeze occurring that brings that moist air inland. And once it meets land, it reaches the air mass reaches the dew point, and it condenses. And it condenses very aggressively. For those of you who've ever spent any time on the West Coast, you'll know that that this type of fog is generally extremely thick. And invasive, and so when we're talking advection fog, I want you to think of sea fog, or think of the West Coast. Upslope fog is simply the clouds that are formed by moist air going up a mountain slope. So as that moisture moves upward, of course, we know the temperature decreases with altitude, and it will decrease to the dew point. It will condense and form a cloud. And then finally, we've got precipitation fog, and this fog is basically associated with a precipitation weather event and the associated evaporation, condensation of that event. So think of like a warm front coming in, and you've got drizzly, steady state, stratiform type precipitation. And as that maybe that warm front meets a colder air mass, now you've got the dry, cool air being introduced to the warm, moist air, and that cool air now becomes moist, reaches its dew point, and condenses. And so precipitation fog is most always associated with frontal activity, some sort of warm air coming together with cold air and producing that condensed state of the atmosphere. But again, it's just same thing that happens in a cloud. The fog, this is just what happens when that cloud, for various reasons that we've talked about here, forms at the surface.